Hello everybody, my name is Thomas Krieger and I want to show how to write deterministic unit tests for multi-threaded Java. Why deterministic unit tests? Non-deterministic unit tests are not really useful. A unit test which fails in 1% or in 1 milli% of all runs is not actually really useful, or a unit test which only fails on a specific machine is also not really useful. So if we say we want to write unit tests, we actually mean we want to write deterministic unit tests. But the problem is multi-threaded Java is not deterministic. So what is the reason why is multi-threaded Java not deterministic? The first thing is thread interleavings. Typically, the outcome of a multi-threaded program depends on the order the threads are executing the different statements. And the second problem is data races. If we have a data race, the compiler might reorder values, or the cause might cache values. So we have those two problems which make multi-threaded Java not deterministic. Let us look at an example to show you what it means that a test is not deterministic. We have a volatile variable j, which we increment by 1 in parallel by 2 threads. And since ++ is not atomic, we expect that the value is sometimes 1 instead of 2. As you see, there is a repeated test annotation, so we repeat the test 100,000 times to see if we actually have cases where the value is not 2. So if we run the test, it takes some time since yeah, we have to repeat the test multiple times. And here we see, yeah, there are cases where the value is actually 1 instead of 2, since ++ is not atomic. And this is actually yeah, what is meant by non-determinism. There are cases, depending on the thread interleaving, where the value is actually 1 instead of 2. Okay, so what can we do? What can we do to solve this problem, to make such a test deterministic? Actually, we have seen one of the first part of the solution. We have to repeat the test. But instead of relying on chance, like hoping that we achieve all thread interleavings by simply repeating all tests multiple times, the idea is to systematically calculate what thread interleavings can happen and then iterate over all thread interleavings. So this is the idea, the solution of this problem, the solution to write deterministic unit tests. We have a while loop iterating over all thread interleavings. And we have the same test. We increment the variable j by ++ inside this while loop, and the same assertion. If we run the test, we see that the test indeed fails. And we see how VMLens works. VMLens runs as a Java agent, and it records all synchronization action and all field accesses to calculate the thread interleavings and to make it possible to iterate over all thread interleavings. So let us look how can we calculate all thread interleavings. Okay, to see how we can calculate all thread interleavings, here's an easier example. Probably the easiest way to make multi-threaded tests, one reading and one writing thread, and using a volatile variable again, and printing out the run number and the value of the variable during each run. If we run the test, we see we have 4 runs. We have one run where we have the value 5, and 3 runs where we have the value 0. Actually, the first 2 runs are used to see what synchronization actions are inside the test. So the first 2 runs are always needed, and the second 2 runs are the runs which execute all necessary thread interleavings. And since we have a read and a write, we actually have first read and then write, and then or write and then read. So this is the way we can calculate thread interleavings. For all dependent operations, like in our example, the read and the write to the same variable, we have to make sure that we always have both interleavings. So in our case, we needed to execute first read and then write, and first write and then read. And this is the same even if we have a more complicated test. We always have to see if we have a dependent operation where the order of the threads matters. We have to execute first the first thread and then the second, and the other way around, first the second thread and then the first thread. And now using this mechanism, we can iterate and calculate all thread interleavings. It of course depends on the type of statement if we need to calculate a new thread interleaving or not. So for example, if we access different objects or different fields, or if we access only with read operations, so I only have for example 2 volatile reads, or if we have non-synchronization actions like a normal field access or a local variable access, the order of the threads doesn't matter, since the threads cannot communicate between each other. So for this case, we simply choose one order of the threads and don't need to iterate to create a new thread interleaving, which reduces the amount of thread interleavings we need to create. So we only need to create a new thread interleaving if the two threads actually can exchange some information. So if the statements between the two threads are somehow dependent. So we need to calculate new thread interleavings, for example, for a volatile read and write, or 2 writes to the same variable. We need to create an interleaving for synchronization blocks. We need to create new thread interleavings for atomic calls to atomic methods of thread safe classes like concurrent hashmap. And for all those cases, we need to look at the order, and therefore we need to create an order between those 2 threads, and need to define them, and basically need a new thread interleaving. We will see later, actually, this is one of the reasons why we can write performant or at least useful unit tests, since we can treat like atomic methods like methods of concurrent hashmap as one block. So we don't have to look inside the method. We can simply, for example, if we have a get and a put of a concurrent hashmap, we can simply execute one where we have first get and then put, and a second one where we have first put and then get. We don't have to look inside the internals of those atomic methods. Similar, basically, if we look at synchronization blocks, we have the operation monitor enter, monitor exit, or monitor exit, monitor enter, but we don't have to look inside those operations and see how the synchronization block is implemented inside the VM. Okay, so let us look at the second reason for non-determinism in multi-threaded unit test databases. The compiler might reorder statements. The CPU might cache values so that we don't see the correct value, but only if the field accesses are not correctly synchronized. So if the statements are not correctly synchronized, this might happen. If it's correctly synchronized, we always see the current value. And a not correctly synchronized field or array access is called a data race. So how can we treat this in our unit test? The idea is we can check if access is correctly synchronized, and if not, we can report in data race, so treat it as an error. And this is what we can actually do with VMLens. So if we remove in this test the volatile modifier, making the field access to a non-synchronized field access, and run the test, we see that VMLens reports an error, reports a data race. So this is the reason why we see the Java agent and then writing events. VMLens does this asynchronously. After the run, it checks all field accesses and checks if there is a data race. So this is the second problem leading to non-determinism. And by solving those two problems, we are now able to write deterministic unit tests for multithreaded Java. VMLens makes this asynchronously. So VMLens generates also a report where we can then see where the database is happening. Here we see, in our case, it's very, very easy. We only have the read and the write from the two threads and no synchronization actions. So this is a typical data race. Okay, so now let us look at the last error type, deadlocks. Here is an example for a very easy deadlock. The order of the locks is different in the access of those two threads. And if we run this as expected, we see that there's a deadlock. The run is actually not ending, so it reports simply that there's a deadlock detected and is blocked. So what's about performance? I think since before we had the possibility to calculate all possible thread interleavings, we had to rely on chance, and therefore we needed many iterations to find an error. But now I think it's getting better. It should work, and it's actually rather fast. And I think we have three ways to improve the performance. One is we should focus on unit tests. So the smaller the test, the easier it is to repeat the test and to repeat it multiple times. The second, for loops, I think the idea is to only look at the start and the end of the loop. So if you have a loop like 100 iterations, we only look at the first iteration and the last iteration. And the third idea is we can treat special classes, for example, Java util concurrent, as a black box. So I think this is the same idea like when we use mocks. We don't need to test concurrent hash map. Java util concurrent hash map. We simply want to test if our code works correctly with the map. So we can treat those atomic classes at black box. And if we take those three parts together, the performance, it actually works, and it's rather performant. Okay, so now after we have deterministic unit tests, the question is, how can we use it to test if a class is thread safe or not? How can we use it actually? And well, in 99% of all cases, thread safe means the methods are atomic. So we see either the value before or after the call, but nothing in between. There are some cases where we have another definition, like for example long adder or long accumulator. But I think for our cases and in the typical case is we want to test that a method is atomic. So in the following we will concentrate on atomic methods. And here's an example, the typical situation. We call the class under test in parallel then to test that the method is atomic. Thread A calls method A and thread B calls method B. And we have again, similar as before for calculating all thread interleavings, two cases. First method A and then method B, or vice versa, method B, method A. And if we then are at thread A, we have to check either method A or method B or method A. Here we see an example of such a test. Test for a class from VMLens itself. Field repository should store the fields and what type of field is it? Is it a volatile, a normal field, or a final field? And we have use cases where we need the ID, and other use cases where we need the ID and set the type of the field. And both methods asInt and getID and setField can be executed in parallel by two threads. So we have the first thread calling getID and setField, and the second thread calling asInt. And here we test in each thread that the value is actually the same as the previous ID plus 1. So as we have seen, in this case, it doesn't matter if the order, the method should always return the same value, independent if the other method was called before or not. But it's an example of a test to test that this method is actually atomic. Here we see the report VMLens generates. We see the name we have given during the creation as we created the while loop. We see the number of runs VMLens needed to execute this test, in this case 4 runs. And we can click on the link to see which synchronization actions were executed. If no data race was found, VMLens only reports the synchronization actions. And we see here we use an synchronized block. So therefore we need only two runs to execute the two thread interleavings, one thread, the started thread, and then the main thread, and the second interleaving, the main thread, and then the started thread. So we needed actually 4 runs, 2 runs to see what synchronization actions are inside the test, and 2 runs to actually execute the all thread interleavings. We have seen how to write deterministic unit tests for multi-threaded Java. We have seen the problem with multi-threaded Java, with testing multi-threaded Java, that it's not deterministic, and we have seen the reasons why is multi-threaded Java not deterministic, and we have seen we can solve this by iterating over all thread interleavings in a systematic way, and we have seen we need to check for data races. This is all done by VMLens in the background. And then to test if our class is actually thread safe or not, we can execute our methods in parallel and then check the result by checking if it's either only the result of the method call, or if there was another thread calling a different method before our method call. So I think, that's actually the way to test multi-threaded Java. Would cool if you connect with me, tell me about your experience developing thread-safe multi-threaded Java, and would cool if you try it. The documentation is on the website vmlens.com. There you can see how to run VMLens with Maven or with Gradle or as a standalone tool. Thank you.